Welcome to another day on the Journey Shake Cam. These two warm-up questions should be reviewed for you, so please do them to the best of your ability, and I'll see you in a moment. In number 1, first we must have a balanced equation. Oxygen plus hydrogen produces water. Now I have seen it where students have started with water and then decomposed it to oxygen and hydrogen. So it's very important that you read the question and respond accordingly. I write down what am I given and what am I looking for. I'm given oxygen, so I need to change my 16 grams of oxygen to moles. 1 mole of oxygen has a mass of 32.0 grams of oxygen. It's very important that you remember your diatomic molecules. I brought clay for our new house because the mass must be doubled. Then I have to change compounds using the balanced equation. This is my recipe. There are 2 moles of water for every 1 mole of oxygen. That gets me to moles of water, and then I change my moles back to grams. And 1 mole of water has a mass of 18.0 grams of water. Now, it's possible to do this in your head. You can see that 16 divided by 32 is 1/2. Times 2 is 1. Times 18 is 18. And therefore my answer is 18. And I go back to my original problem, and my least number of significant digits is 3, so I need 18.0 grams of water. And that's how you do number 1. In number 2, we have one of my most favorite equations. You must know your decompositions. This one is a metallic chlorate, and whenever I decompose a metallic chlorate, I always get a metal chloride and oxygen, and then I must balance the number of atoms, because based on the law of conservation of mass and energy, I must have the same number of atoms on both sides of the equations. Now in this problem, I am given 2.5 grams of the potassium chlorate, and I want to find the mass of the oxygen. I take my 2.5 grams of potassium chlorate and change it to moles. And 1 mole of potassium chlorate has a mass of 122.6 grams. Now, potassium is 39.1 and chlorine is 35.5. And there are 3 oxygens, which is 3 times 16.0. So I write them again because remember, that's where many mistakes occur. I write them all out and I get 122.6 grams per mole. That's how I change my grams to moles. Now I need my mole ratio from the balanced equation. I'm finding oxygen and I want to cancel my potassium chlorate. And then I change my moles back to grams. And 1 mole of oxygen has a mass of 32.0 grams of oxygen. 2.5 divided by 122.6 equals times 3 equals divided by 2 equals times 32 equals. And the number here is 0.9787. I go back to my original problem and I want 2 significant digits. I look at the 3rd digit to determine if I round up or not. And therefore my answer is 0.98 grams of oxygen. That's my final answer. Now we're going to learn something new, and you know how much I love that. And we're also going to use the information on a lab that we're going to do in a couple of days. This is all about specific heat. And specific heat is the amount of heat that a substance can absorb for 1 gram of the substance to change 1 degree Celsius. Now the formula that we use here is that heat equals the mass times the change in temperature times the specific heat capacity of the substance. Mass is given in grams, the change in temperature is in degrees Celsius, and our specific heat capacity is in joules per gram degrees Celsius. Now a joule is the scientific international unit for heat. And oftentimes we use kilojoules when we have a very large number. And there are 1,000 joules in 1 kilojoule. But for specific heat, we use joules per gram degrees Celsius would be the unit. Now the specific heat for water is 4.18 joules per gram degrees Celsius. That's a very large number. Most metals have less than 1 specific heat capacity, and water has a very large specific heat capacity. And this is one of the reasons why when you live in a coastal area that the temperatures are more moderate, because the waters absorb a lot of heat. And if you're in an area in the middle of a country, then that land mass does not absorb as much heat and it releases the heat, so you can have very large temperature changes very quickly. I thought that was a little interesting point of information. So we know that this equation is our equation for heat, and sometimes we see a Q here instead of an H. I prefer H. Now we also know that when we use what's called a calorimeter, which is a method by which we are going to measure how much heat something may have, we're going to use the idea that the heat gained is equal to the heat lost. And this is what we're going to use in the lab. Now I know that the heat gain being equal to the heat lost, I'm going to use this equation here. And so I have mass times the change in temperature times the specific heat capacity equals the mass times the change in temperature times the specific heat capacity. Now what we're going to do in the lab is, here's a little picture of my lab setup. I am going to take a metal that I know what metal it is, and I'm going to drop it into boiling water. And water normally boils at 100 degrees Celsius. And so my metal, the temperature, because metals are conductors, it will very quickly absorb that amount of heat and also become 100 degrees Celsius. Then I will remove it and put it into a styrofoam cup that I have filled with water. And the water will be approximately room temperature, which is 24 degrees Celsius. Now, when I take this metal and put it into the water, the temperature of the water will rise. So that will be my heat gained, will be the water. And the heat lost will be my metal, because the metal will cool off. Now, the metal, once I put it into the water, this temperature of the water is going to increase only a couple of degrees. So let's say that it goes up to 27 degrees Celsius, and that would be called my final system. This is the final system. So I put my metal into the water, and the water goes up by 3 degrees. So my equation here, I'm going to be solving for the specific heat of this metal. That is my unknown. And by rearranging these values, I can say that the mass of the water, W is for water, times the change in temperature of the water, times the specific heat capacity of the water, divided by, because undoing multiplication, I'm going to divide by the mass of the metal and the change in temperature of the metal. The change in temperature of the water is going to be 3 degrees Celsius in this example. And the change in temperature of the metal will be 73 degrees Celsius because it went from 100 to 27. And so the change in temperature of the metal will be 73 degrees Celsius. And that's what we're going to be doing in the lab on specific heat. And it's a very simple, but yet very, very important lab. And I know that you might have seen it before, and that's very good. That shows you how very instrumental this is in understanding heat capacity. Now, this next thing, I want to introduce it for you because it's a difficult concept and students seem to have difficulty understanding exactly. So I want to introduce it slightly today, and then I will discuss it again tomorrow so that you have some time to sleep on it and try to see if maybe you can assimilate it in. Now, oftentimes if we're baking a cake, my recipe might call for 2 eggs and 3 cups of flour. But if I only have 1 egg, I can't make the whole recipe. I could only make half of the recipe because I only have half of the ingredients. So I would have to adjust the other ingredients and only use 1.5 cups of flour. And the one that I'm going to run out of is called a limiting reagent. And the one that I have plenty of is called an excess reagent because it's left over. And when we have this in chemistry, I'm going to use the equation that we had from the warm-up where we made water. And I have 2 grams of hydrogen and 2 grams of oxygen, and I want to know what mass of water can be produced. And therefore, I don't know which one of these 2 is going to run out or if one will run out. Therefore, I must change them both to moles because I only can make a comparison between compounds as moles. And 2 grams of hydrogen, I change that to moles. 1 mole of hydrogen is 2.0 grams of hydrogen. Therefore, I have 1 mole of the hydrogen. Now, I have 2 grams of oxygen, and 1 mole of oxygen is 32.0 grams of oxygen. Therefore, I only have 0.0625 moles of the oxygen. Now, just because this number is less does not mean it's going to be my limiting reagent. Sometimes it is, but I need to make sure that I determine it based on the information that I'm given. Now, what I do is I call my balanced equation the recipe. And these moles is what I have. It's like what I have in my cupboard. I only had 1 egg, and I only have this amount. Now, I always pick the first one that I get to, just so that I'm always doing things in the same pattern. Now, my ratio here is that there are 2 hydrogens in my balanced equation, so I'm going to use my recipe. 2 is to 1, as 1 is to my unknown. Even though this is what I have, I want to know how much it would require to use up this 1 mole of hydrogen. This 2 and this 1 are my 2 and my 1 from my recipe, from my balanced equation. So 2 is to 1, that's what I have. 2 is to 1, as 1 is to what? I want to know how much it would take to use up this 1 mole. Then I do the math. 2x equals 1, x equals 0.5 moles of oxygen would be required to use up this 1 mole. Well, I don't have that much. I only have 0.06. Therefore, I am going to run out of oxygen because I don't have the amount that it would take to consume this 1 mole of hydrogen. Therefore, my oxygen is my limiting reagent, and hydrogen is my excess. Now, the importance of this is that I would then use my oxygen to determine how much water, and we did that in the warm-up. And you will recall that when we did that, we got 2.3 grams of, no, we got 18.0 grams of the water. That's what we got in our warm-up. So I don't need to go through the rest of that process. I merely want to introduce limiting and excess reagents. Now I'm going to give you one more example. In this example, we're going to have ammonia. We are going to produce ammonia from its elements. So nitrogen plus 3 hydrogens gives me 2 ammonias. Now I have 14 grams of the nitrogen, and I have 2 grams of my hydrogen. So I change my 14 grams of nitrogen to moles. And 1 mole of nitrogen, because it's diatomic, we have to remember our diatomic molecules, is 28.0 grams of nitrogen. Therefore, I have 0.5 moles of my nitrogen. I have 2 grams of hydrogen, and 1 mole of hydrogen is 2.0 grams of hydrogen. Therefore, I have 1 mole of my hydrogen. Now, once they're in moles, I can compare them to my recipe. This is my recipe, and this is what I have. So I say, I always pick my first one. There is a coefficient of 1 in front of the nitrogen. So 1 nitrogen is to 0.5 as 3 is to X. 1 is to 0.5 as 3 is to how much? That's what I need to know. In order to use up all of this 1/2 mole, how much hydrogen would I need? Well, I would need X equals 1.5 moles of the hydrogen. And I see that I only have 1 mole of hydrogen. So therefore, hydrogen is my limiting reagent. And nitrogen is in excess. And then I would use my limiting reagent to determine how much of my ammonia could be formed. And then I would have 2 moles of ammonia is 3 moles of hydrogen, and 1 mole of ammonia is 17.0 grams of ammonia, because nitrogen is 14.0 and there are 3 hydrogens. 3 times 1.0 is 3, and 14 gives me the 17.0 grams per mole. I always must determine the amount that can be produced based on the limiting reagent. I can only make as much of that cake as I have the least amount of the material, and I ran out of eggs, so I could only make half of that recipe. So I wanted to start you with that idea of thinking about limiting and excess, because tomorrow we'll have some more practice on this, and I just wanted you to kind of introduce those ideas to you. Limiting and excess reagents, because I believe you've probably seen those terms, and now this should make more sense to you. Well, that was some fun, and I know that you love those challenges, and I know you're going to be good at it, so please do worksheet C for tonight, and we'll see you tomorrow.